moving on with life. The intermediate value theorem. So this is a nice little theorem. It's a very intuitive theorem, surprisingly difficult to prove, so we won't prove it, but we'll state it and you'll be like, oh yeah, that makes sense. And then we'll use it to talk about the bisection method. So let's write it down. It's a theorem. Let's see. Okay, so suppose f is continuous on a closed interval from a to b. Then for any number, let's see, how about, what letter would you guys like? Q. Okay. Q. Any number Q. For any number Q in between f of A and f of B. Okay, now this is important. So this is just like a note, mid-theorem note. If you think of this graphically, what is Q? What does it represent? It is, so notice it says it's in between f of A and f of B. So this interval right here, this A to B business, what are those? Are those x or y values? These right here, the A to B. Those are x values, right? But what are f of A and f of B? Those are y values. Those are the values of the function, right? So these are y values. So Q is in between f of A and f of B, right? So that means Q is a y value. Okay, so, but it can be any y value between f of A and f of B. Yeah? Okay. All right, so that was just like a bit of a, just to make sure we're on the same page. Okay, so for any number Q in between f of A and f of B, there exists some, let's say C. Well, I guess since we said number, some number C. Okay, now to make the point here, what is C? X or y value? C is an x value, right? Okay. Such that f of C equals to Q. Okay, so I'll draw a picture of this. It's pretty straightforward. So basically, let's say you have the following. You have some interval, A and B, sorry. And let's just kind of walk through this. So you have some function, and we know that it's continuous on this interval, right? Now let's just say hypothetically f of A is right here. So here's f of A. Is that y value, right? And then let's just say f of B is right here. Let's say it's that right there, right? And then, you know, the function can be doing whatever, and then maybe it has a discontinuity there and whatnot and what have you. But you know for sure that between A and B, it is continuous. Yes? So here after this, it can, you know, go off and do weird things and whatnot, but it doesn't have to be weird. I'm just saying that it can be weird outside of the interval that we're looking at. Okay? Now, so what is this theorem saying? The theorem says that for any, so if you pick any number Q, so any y value in between f of A and f of B. So what are you looking at? You're looking at right here. So pick any y value in this interval right here. If you pick any y value in there, you're guaranteed that there's going to be an x value here somewhere such that when you plug in the x value into the function, you get that y value. And I mean, that makes sense, right? Because basically, I mean, if you think about this, so right here I kind of left it blank. But how can you possibly get from this point right here to this point right here if you know for sure it's continuous? Is there any way for you to get from here to here and skip one of these y values in between? Is it possible? It's not possible. Why is it not possible? Because it's continuous, right? So if it's not continuous, well, then maybe it could jump, or maybe you can do some weird thing, right? But if it's continuous, well, then for sure you're 100% guaranteed. You pick any y value in here, and you might only find one x value that corresponds to it. You might find more than one, but you're guaranteed at least one. Does that make sense? Okay. All right. So let's use this for something here. So one of the really nice applications of this is called the bisection method. Bisection method for root finding. And you know how, like, in your calculator, so most of you guys probably have like a TI calculator, right? And when you so you don't actually have to draw this. I just don't have one to show you, right? Do I have one? No, I don't. Okay, but let's say so please don't draw this. This is going to be terrible. Okay, so you have this right here, right? And your calculator has some buttons, and you graph your thingamajigger, and then it has a, what is it called? A 0 button. Have you guys ever used that? Like you go to math or something, and you hit 0, and then it asks you a question. You guys remember what the question is? Yeah, it asks to say, oh, what's the left bound, right? And then what's the right bound? And then it asks you a guess. Now, the bisection method does not use a guess. That'll be Newton's method, which we'll see later on. But what it does is it basically takes the left bound and the right bound, and then it just, it doesn't use like an actual brain, like a person thinks of a brain. It's like, oh, it's right there, or let me do the quadratic formula, and then I'll find the root, or whatever. What it does is it takes the interval. Well, this is what the bisection method is. So I'll just explain it this way here. So the bisection method, and later on we'll talk about Newton's method. But basically you have this. Let's say you plug in a point right here, and then you plug in, so the calculator does this, right? So it's like, oh, here it's positive, and here it's negative. What does that tell you? What has to be true about in between the two? Has to be 0 in between that interval, right? And so then what it does, but computers are really fast, right? So it doesn't take this long to do this. It splits it in half. And then it goes, okay, here it's positive, here it's positive, here it's negative. What subinterval is it on? Is it on this first one or the second one? It's going to be right here, right? Because it's positive here, negative here, so then it has to go through 0 in that interval. And then what does the computer do? Yeah, so it just keeps doing this, and then when does it stop splitting it up? It splits it, it splits it, it splits it, and then it stops as soon as it's accurate enough, right? Now, when you do this on your calculator, it seems like it's just instant, right? But what the calculator does, it'll do it a whole bunch of times, right? Thousands, millions, whatever number of times it needs to do. And it'll hone in on the actual 0 itself. And what is the bisection method based on? The intermediate value theorem, right? Right? Basically, I mean, that's what it is, right? It has to pass through 0. If you know it's positive on one side, negative on the other, has to pass through 0, right? Because you're guaranteed to pass through every y value in between. Okay, all right. Well, Okay, so now let's do the bisection method. Okay, so bisection method. So we'll do it by hand, just to get the practice of what it looks like. But keeping in mind that this is a job better suited for calculators, well, computers really. So let's do an example. So let's say, for example, so let me pick one here somewhere. I had a good one over here. Let me see. Where did it go? See, now I lost it. Okay. All right, so you have this function, and so this interval from 0 to 1, that would be like if we were going to plug it into our calculator, that would be like our left bound and then our right bound. So the idea is, so all you really have to do, well, first of all, is this function continuous? Yes. So f is continuous. Why? Since it is the sum of, what kind of function is that? Are exponential functions continuous? Sure. Okay. Exponential functions, and what kind of function is that? 2x minus 3. And a linear function. Okay. So what does that mean? Well, then that means that we can use the intermediate value theorem, right? If it's not continuous, well, then you can't assume that that you're going to have that behavior where if you test at one point it's positive, the other point it's negative, you can't guarantee that it's going to be 0 in between, right? Only if the function's continuous. Okay, so let's see. So let's write something like this. Let's say step 1. So what we do is we plug in 0 and we plug in 1. Okay. So let's see here. So all we care about at this point is not what the y values are, but the sign of the y values, really. So if I plug in 0 here, what do I get? I get e to the 0 plus 2 times 0 minus 3. Is that positive or negative? Okay, so that's less than 0, right? And then if I plug in 1, is that positive or negative? So remember, e is about 2.7, right? So 2.7 plus 2, that's 4.7-ish. That's positive, right? Okay. All right. Now, what can I say? Because they're opposite signs, that means that it... Yeah. So this means that it must equal... So this is like just notes for you, really. Must equal 0 on the interval between 0 and 1, right? Okay, so that's the first step. Now, after that, what are we going to do? We're going to basically split it. So let's see. So let me draw, maybe it'll help if I draw a little picture here. So you have the number line here. This is 0. Here's 1. So what we do is we split it right here. Bam, split. What's right halfway between 0 and 1? A half, right? 0.5 or 1/2. So let's see. If I do, well, I'll just write it as 1/2. Okay. Now, I plug in f of 1/2. Okay, so this is where it's very important. I plug in 1/2. And what's the sign of this? So e to the 1/2, that is square root of e, square root of 2.7. So can we tell? We might need to plug it into our calculator, but so this is 1 minus 3, this is minus 2. It's negative? Okay. That would be my guess, that this is less than 2. Okay. All right. So now this is very important. So what does this tell me together with this information right here? Where's the 0? In between 1/2 and 1. In between 1/2 and 1. Can you guys see why? Because it's negative at 1/2, right? So it's negative here. So it's negative. Let's say this is the dot right there. And then where is it positive?
1.
At 1, right? So it's positive at 1. So these dots represent the y value. So here, notice from 0 to 1/2, is there a 0? So, okay, important question. Is there a 0 between 1/2 and 1? Yes, absolutely, right? Guaranteed. Guaranteed because it has to go through here somehow, right? Okay. Is there a 0 from 0 to 1/2? Okay. Guaranteed. Not guaranteed, right? Because it is possible, now it probably isn't in this function, but it is possible that it does this, right? Can it do that? So that's what the intermediate value theorem. So if it's positive on one, negative on the other, you're guaranteed that it's going to go through 0. If it isn't, well, it may or may not, right? So you would have to then take a look, but you're not guaranteed one or the other. Does that make sense? So it's important to make the distinction. Okay. All right. Let's see. So then, how would I? So now notice my interval. I started an interval of length 1. Now I've narrowed it down to an interval of length 1/2.
Split quarters.
I can now split it again, right? So what would be my step 3 here? 3/4. Yeah, make sure you're careful because I want to test in the interval that I'm sure there's a 0, right? So I'm now going to split. This would be my split right here. Split. So if I plug in 3/4, what do I get? I get... That's positive? Is it positive? Yeah? Okay. All right. All right, so now what's my interval now? 1/2 and so let me see here. So here it's positive, right? What am I looking for? Where it's negative, right? This one right here. So notice how it's negative at, so this was 1/2, right? So it has to be between 1/2 and 3/4. What stops me from going back to this one where it's negative as well? Where was it? 0. Why would I not go all the way back there? We've already narrowed it down to this interval, right? 1/2 to 1. You forget about all this stuff. This one, forget about it. You still look at 1, right? So basically, when I test here 3/4, what am I comparing? I'm comparing this. I'm comparing 1/2. I'm comparing 1, and I'm comparing 3/4. What did I find? Let me see. I found that at 1/2 it is negative, right? At 3/4 it is positive, and then at 1 it's positive. So where am I guaranteed? Between 1/2 and 3/4, right? Does that make sense? Okay. So now I've narrowed it down to 0.25 accuracy, right? So obviously this is not something that you would do like an actual person would do as a way to approximate a 0 manually. But it shows you what your calculator actually goes through, because the computer can do these things over and over again really easily, you know? Does that make sense? Any questions with the bisection method? Does it make sense? Does it? Yeah?
What is our application of that? Just knowing it? Knowing how it works?
Yeah, I mean, of course I can ask you to do it, but I'm just saying that in reality, doing something like this would be, I mean, I guess the actual application would be you actually programming a computer to do it, for example. Taking some mathematical procedure and then coming up with an algorithm to tell the computer to do it is valuable. And it's as we go through more of this stuff, when you use the calculator buttons, it's like nice to be able to get the answer right away. But it's also not, much better to really understand what the calculator is actually doing to get the answer. How does that actually work? So this is just one of the small pieces of doing that.
So like you wouldn't want us to like sit there and calculate it out to actually what the answer is just because the amount of time it would take to do by hand, but this just rather just showing us how the function operates.
Yeah, I mean how it works, but I mean I could ask you to do it, but it's not really a fruitful use of your time. What is it?
By hand, did you ever get to it, or would you have to keep splitting?
Well, you can. You would keep splitting forever.
Oh,
yeah. But that's the thing. It's not very fast, right? I mean, so basically, your interval gets halved every time. Which, if you want, good accuracy. Let's say you want it to be, 6 decimal places of accuracy. That's going to take a while. So you don't want to do that by hand. But for example, Newton's method, which we'll see later on after we've looked at derivatives, that'll get accurate much, much faster than the bisection method can. And you can get really accurate. So whereas here we did, say, 2 steps maybe. How many did we do? 3 steps. And our accuracy is still pretty bad. With Newton's method, you can get really close with just doing a couple steps. And then if you do more, then you can get pretty close. I can show you the idea of Newton's method if you want. You guys interested?
Sure.
For fun. Newton's method idea. We won't actually be able to do it, but you can get the idea. What you do is you say, so like let's say for example, so just to draw some function here, f, and so I don't know, let's say this is a, and then here's b, and then, so this is actually how the guess thing works. So here's a, here's b. Okay, all right. So okay, hold on. Okay, so okay, pick a guess. So I'm gonna point my finger, and you guys tell me when to stop. Where the guess is, right there. So like imagine you're in your calculator, and you're just like, oh, left bound, it's right there, A, and then right bound, it's B, and then you guess, right? Typically you kind of get close to it, right? Mm-hmm. Okay, so let's say we pick right here. Yeah? Mm-hmm. Okay, all right. Okay, this is my guess. Guess. You just need a point to start. So it's right there. Yes? All right, so the way Newton's method works is wherever you guessed, what you do is you find what's called the tangent line. So it's a line that is tangent to the graph. So think of just barely skimming the surface. Like when what's that thing called? That board? Or like when you skimboard, right? Or like when you throw a rock into the lake, and you make it skid. Yeah, so it's like that. Okay, so we're gonna talk about this later. But anyways, okay, so you got this line right here, like this. So this is called the tangent line. This tangent to the graph looks like that at that point. Okay, then let's see here. Purple. Okay, so here this line crossed the x-axis right there. Yes. So now you use that as your new quote-unquote guess, and you do the same thing right there. Okay, so notice I did one. This is one step right here. This is 2 steps. So here you just repeat it. So now, and see how close you are just by doing 2 steps? You're already pretty close. So that's the 0 right there. And you're already pretty close just by doing 2 steps of the Newton's method. Yes?
And I know we haven't learned the math for it yet, but is that where the difference quotient comes in for tangent?
Well, the difference quotient allows you to find the derivative, and the derivative is what you use to find the tangent line, and the tangent line is that line right there. So yeah, we'll use it for sure. Oh my gosh, it's doing that thing again. I don't know how to make it stop. I just want to zoom in. Right there. Okay, so see how close I am? And then notice, stop it. Stop moving. I don't know why it's moving. Okay, and then so see right there, it crosses. Ah. It's leaving. It's like a train. It's leaving the station. But then so see already, so with 3 pretty much you're like right on top of it. And you'll see when we get to it and we actually go through a couple steps, you'll see that you get really good accuracy just by doing it a couple times. And then if you want really, really good accuracy, then you just keep doing it, if you want. So pretty cool stuff, right? Okay. All right. Well, why don't I give you guys one to try? You guys try one. Can you guys try one? Try. Let's see. So, let's see. Let's see. How about sin x minus x squared plus x on the interval between 1 and 2. To the nearest quarter, let's say. So basically how the number that we, so you'd have to do it 3 times, right? From 1 to 2, so split it in half. 3 times, I guess. Okay, so give it a go. All right, so let's see. So you plug in 1, you get positive. Okay, I'm trusting you guys on this. Okay, negative. All right. So then, okay, so this tells me that it's between 1 and 2. Okay, well, I already knew that, right? Okay, and then you plug in 3 halfway, right? So 3 halves. And what is that? What'd you guys get with 3 halves? Positive? Oh my gosh. Can't be getting opposite signs there. There's only 2 choices. One or the other. Some conviction.
Negative.
Negative? You sure?
Yes.
Make sure that it's in radians. Okay, negative. All right. So what does that mean? That means that it's between 3/2 and 1, right? Because it's positive, negative. Yes? Okay. All right. So between 3. Oh. Well, yeah, between 1 and 3/2, right?
I got positive.
I got positive too.
Yeah, positive. Because I got 0.247.
Yeah, I got 0.247.
Okay. Going back here. Positive. So that means that it's between 2 and 3/2. Okay, all right. Okay, so then I split this one in half, right? And I plug in, so what would that be? Halfway between 3/2 and 2. Okay, 1.75. All right, what is that? That is negative, you sure?
1.625.
What is it?
This is 6/4, so it leaves you with -3/4.
Is 1.75, when you plug in 1.75 into the function, do you get a positive or a negative?
Negative.
Sure? Positive 100%?
Please make sure.
Negative 100%.
I got a negative. Yeah, negative.
A negative what? Okay, okay. All right, so then what does that mean? That means that it's between 3/2 and 1.75. Yes? Well,
Really? Why couldn't it be less?
well, I don't know. I just used the numbers you guys kept giving me.
Yeah, it's negative.
All right, what's the actual one? 1.6 you said, Calvin?
No, instead I got negative between 1.65.
Between what?
I still got a negative of 1.625. The sign at 3/2 is 0.99. Like 0.997. Negative to 3/2 squared is minus 9/4 plus 3/2. So negative 9.
All right, let's see if we did it right.
Leaves you with 3/4. So 0.99 minus that is like 0.2.
Oh, boo. All right, let's see if we did it right. Oh, yeah, 1.6. Yeah, that's not bad. It says right there, it's 1.6. See? And that 1.6 is between 1.5 and 1.75, so we must be on the right track. Okay. All right. Well, hey, good times, guys.